Hello, we are the General Dynamics Electric Boat Capstone team. Our project is on transmitting low frequency radio frequency over fiber optics. Our team consists of Amanda Idavea and myself as Zachary Hansen. We are both majoring in electrical engineering. Our technical director is Mike Bronner, a staff engineer at Electric Boat, and our consulting technical director is Mike Smith, founder designer of Bold Circuits. Electric Boat was founded in 1899 with their first submarine in 1900, the USS Holland. Currently, they are building the Virginia-class submarine and are contracted to build the new Columbia-class. Electric Boat is a large company with over 14,000 employees at 8 different locations across the United States.
The motivation for our project is to communicate between buildings and radio towers utilizing low-frequency radio waves. By utilizing fiber, we hope to reduce latency that can improve system performance and allow for longer cable paths compared to coax cables. Our anticipated best outcome is a functioning prototype proving the ability to transmit low-frequency radio frequencies over fiber. The system must be able to recreate the signal after transmitting it across 1.5 kilometers of a fiber optic cable. The system must also have very low bit loss and less latency than coax cable. With the successful completion of our project, Electric Boat will be able to remove coax cables and replace them with fiber due to the many benefits fiber offers over coax. It has long-distance transmission and is cost and energy efficient due to it not needing amplification like in coax cabling. Fiber also travels at the speed of light, reducing latency. The biggest benefit of fiber is that it is not affected by electromagnetic interference, which can distort the signal if cabling is not properly shielded. Our technical accomplishments so far started with research. Research was a large part of the beginning of the project due to our lack of fiber optic classes and overall knowledge. We need to cover the different modes, how it communicates, and how to connect fiber along with analog to digital and digital to analog converters that can help achieve our goal. Then we got started working on our MATLAB simulation. We created a signal that passed through a 12-bit ADC in a simulated fiber transmission and then converted it back to a digital signal to send through a 12-bit DAC, replicating our original signal. Now we are in the process of building the prototype, utilizing an Arduino Mega that will interface with the optical transmitter and receiver using a UART connection in addition to our ADC and DAC utilizing SPI communication. As you can see here in our block diagram, we start with a 10 kilohertz signal and send it through our 12-bit analog to digital converter that will then go through the optical transmitter. That signal will be transmitting over 1.5 kilometers of single mode fiber. From there, it will go into an optical receiver and a 12-bit digital to analog converter, outputting a signal identical to the original input signal. My technical accomplishments began with a heavy amount of research. Our signal will be transmitted to light and will be traveling through the nanometer thin core shown in the picture to the right, which required us to have an understanding on how to transmit and receive over fiber. Research was also needed to learn about ADC and DACs to choose the correct process of conversion for this project. After my initial research was complete, I used ADC and DAC equations to validate the equivalent input and output signals, along with the ADC and DAC to meet the requirements set by the company to ensure we meet our anticipated best outcome. Here you can see our analog signal with noise built in to demonstrate our ability to replicate our signal in MATLAB. As you can see in the bottom graph, our ADC is sampling at 12 bits, recreating the signal perfectly and proven to be equivalent to the analog input by the equation provided below. For my future accomplishments, I will begin by programming the Arduino using C++ while utilizing SPI interface to communicate with the ADC and DAC. The optical transmitter and receiver will be using UART connections to interface with the Arduino. In addition, I will be assisting with the prototype assembly and its testing.
My technical accomplishments started with the research into the different modes of fiber and their properties. Then I looked into ADCs and DACs, ensuring we used what would work best for our project. I created a MATLAB code that simulated a source signal that has noise, making it as realistic as we can for a simulation. Then I created a 12-bit ADC and a DAC, and in between them created a simulated optical transmission, thus creating a simulation of our project. Finally, identified the parts required for our prototype. My future accomplishments are to build the prototype, program the Arduino to process the signal, and test the system's capability to ensure it works properly. To accomplish our anticipated best outcome, we still need to program the Arduino using SPI for the ADC and the DAC, interface with the optical transmitter using UART. We also need to assemble the prototype and test each part individually and as a whole system. The biggest risk to our project are the programming of the Arduino and the testing of the fiber. The Arduino code is going to be complex and challenging to perfect. Due to not having the ability to test fiber currently, we do not know if we will be transmitting or receiving properly over fiber. A special thank you to Mike Bronner and the General Dynamics Electric Boat for sponsoring our project. And of course to Dr. Sunak, Mike Smith, and the ELE Capstone team for this real-world work experience.